Let's study 9th standard ICSE physics, exercise 2C numericals.
Now here question 2 can be cancelled, it's too easy, and even 6th. Mark IMP, 7th sum, 12th, 14th and 15th, they are IMP. Let's start with this third sum. A vehicle is accelerating on a straight road. Its velocity at any instant is 30 kilometers per hour. After 2 seconds, 33.6, and after another 2 seconds it is 37.2. So initial velocity was 30, then after 2 seconds it became 33.6, and then after another 2 seconds it became 37.2. So clearly there is an acceleration, but we have to calculate the acceleration. So we have two cases here. In case 1, initial velocity is 30, final is 33.6, and in case 2, initial is 33.6 and final is 37.2. Now instead of converting each into meters per second, what I'll do is I'll take the difference between the u and v, and this difference of 3.6 kilometers per hour, that will be converted into meters per second by multiplying by 5 upon 18. And then the acceleration is the difference upon the time. So 1 upon 2, because time is 2 seconds, gives me acceleration of 0.5 meters per second squared. And even here I get the same acceleration because the difference in the velocity in equal intervals of time is equal. Therefore, the acceleration is uniform. Now in the 7th sum, a train travels with a speed of 60 kilometers per hour from A to B, and then comes back with the speed of 80 kilometers per hour from B to A. Calculate the average speed. Now if you feel that the average should be 60 plus 80 upon 2, that is 70, that's not right. That's not the way we calculate speed. What we'll do here is, table method is the easiest method. So A to B speed is 60 kilometers per hour and B to A is 80. Let the distance be x, since the distance will be the same. We should not take distance as 1 because that's an assumption which is not allowed. Now we know the time formula is distance upon speed, so we get the respective times of the two journeys in hours. Now the formula for average speed is total distance upon total time. Total distance is x plus x to x, and total time is this plus this. We'll have to take LCM out here. The LCM is 240. So into 4 into 4 and into 3 into 3. So this is the denominator. I'm using brackets. Denominator goes to numerator. Fortunately, x and x gets cancelled. And on calculation, we get the average speed as 68.57 kilometers per hour, surprisingly, not 70. And the average velocity is easy. Since it came back to the original position, the average velocity is indeed 0 because displacement is 0. And average velocity is displacement upon time. So you can directly write 0. Now in question 9, a car travels a distance of 100 meters with a constant acceleration and average velocity of 20 meters per second. And the final velocity is 25 meters per second. Find the initial velocity, that is u, and acceleration. So let's write the data first of all. That makes this some easy. Displacement is given as 100 meters. Average velocity is given. And average velocity formula is u plus v upon 2. But this is true only if acceleration is uniform or constant. The final velocity is given. So substituting this value of v in this equation, we can get the value of u. So u is 15 meters per second. Next, we want the acceleration. Now there are three kinematic equations that we know. V is equal to u plus 80, but time is not given in this sum, so we can't use that. Then we have S is equal to ut plus half at square. Again, t we don't know. So the only possible equation which can be used is v square is equal to u square plus 2as. We know v, we know u, we know s. So solve and get the value of a, which is 2 meters per second squared. Now the 12th sum. A body moving with a constant acceleration travels distances 3 meters and 8 meters respectively in 1 second and 2 seconds. So two distances are given and two times are given, and what is asked is initial velocity and acceleration. Since displacement and times are given, the formula to be used is S is equal to ut plus half at squared. Since there are two cases, we get two equations in two variables. A is unknown, u is unknown, and a and u is unknown even here. Here we took LCM and I got this equation, and here divide the equation by 2 to get these two equations. And whenever we have two equations in two variables, we can solve them simultaneously to get the values. So here I'm going to subtract the two equations. So a and a gets cancelled. 2u minus u is u. 6 minus 4 is 2. And once you get the value of u, you can substitute it in this equation to get the value of a as well. Next, the 14th sum. A spacecraft flying in a straight course with a velocity of 75 kilometers per second fires its rocket motors for 6 seconds. Now, such big sums need to be read very slowly and with a lot of focus, perhaps even twice. Because only if you understood the sum and you can visualize the motion, only then can you solve it quickly and correctly. So this is the initial velocity. The rocket motors were switched on for 6 seconds. So for 6 seconds, there will be a uniform acceleration, after which the final velocity was 120 kilometers per second. So first of all, find the spacecraft's average acceleration while the motors were firing. That's easy. Acceleration is equal to v minus u upon t. Don't convert the kilometers, it's okay. You'll get the acceleration as a kilometer per second squared. So Roman number 1 was easy. But Roman number 2 is the total distance traveled by the spacecraft in the first 10 seconds. But the motors were switched on for only 6 seconds. That means for the first 6 seconds there was acceleration, and for the next 4 seconds there was no acceleration. The engine was switched off, so it will move with constant velocity. Yes, it will not slow down because there is no friction in space. Now I prefer to do this Roman number 2 graphically. So first we'll draw a graph which helps us to understand the sum very well. So the initial velocity was 75 and the final velocity is 120. For the first 6 seconds there is an acceleration, a uniform acceleration, as you can see. It's a VT graph. And after that there is uniform velocity. So from the 6th second to the 10th second there is a uniform velocity, which is 120 kilometers per second. Now acceleration, I've already told you, for the first 6 seconds acceleration is v minus u upon time. Of course here there is no acceleration. But in Roman number 2, if they want to find the total displacement, from a VT graph, displacement is nothing but area under the graph. So we have to calculate the two areas, area of number 1 and area of number 2. And if we add them, then we can find the total displacement. So when time is 0 to 6 seconds, displacement is the area, which is half into sum of the parallel sides into the distance between them. That is area of trapezium formula. That is half into 75 plus 120 into the height. Height is 6. So we get 585 kilometers as the answer. And for part 2, again the displacement from the 6th second to the 10th second is area, which is length into breadth. Length is 120 and breadth is 4. So 120 into 4 is 480 kilometers. So these are the two displacements. We can add them and we can get the total displacement in 10 seconds is 1065 kilometers. If you don't want to use graph and you want to do it using the kinematic equations, then we can use the formula here. S is equal to ut plus half at squared. U is 75, time is 6, and a we know, and the time again is 6. Or an easier formula will be v square is equal to u square plus 2as. So we know final velocity, initial velocity, and the displacement, and the acceleration, that is 7.5. So we can find the displacement. Similarly, even for the second part, that is from 6 seconds to 10 seconds, we can find the displacement. And this time, since there is no acceleration, the displacement is simply the velocity into time, the normal formula. So again, if you use these two formulae and you can add them, you'll get the same answer. Next, the 15th sum. A train starts from rest and accelerates uniformly at a rate of 2 meters per second square for 10 seconds. Then it maintains a constant speed for the next 200 seconds. And then the brakes are applied and the train is uniformly retarded and comes to rest. Find Roman number 1 maximum velocity reached. The formula for that is v is equal to u plus at. U was 0, it's at rest. A is given, time is given, so we can find v. But I prefer using the graphical method again out here, because it helps me to understand the whole sum at one go. So I know that initially the train was at rest, and for 10 seconds there was a uniform acceleration of 2 meters per second square. So it reached a maximum velocity after 10 seconds, which we don't know. Then for the next 200 seconds, that is still 210 seconds, it was traveling with that same uniform velocity. There was no acceleration here. Then here the brakes were applied, and in the next 50 seconds, it came to a stop. So velocity was again 0. So first of all, the final velocity, that is the maximum velocity here, is 20 meters per second. So that's what we found out, 20 meters per second. Next, they want us to find the retardation. Again, the formula is A is equal to V minus U upon T. But what was the initial velocity here? Of course, it was 20. This is 20. That's what we found out. And what is the final velocity here? 0. And what is the time? 50 seconds. So substituting these values, I get acceleration for the negative slope here as minus 0.4 meters per second square. But retardation, we write it positively. And the final question is, Roman number 3 is, what is the total distance traveled? And that's where I prefer graph. It makes it so easy because the total displacement is nothing but the area under the graph, that is area of trapezium. That is half into sum of parallel sides, that is half into 260 plus, how much is this now? 200. And the height is 20. So just substitute those values and you get the total distance at one shot. If instead we want to use the kinematic equations, then we'll have to divide it into 3 parts. Find the displacement of this by using the formula S is equal to ut plus half at square, or v square is equal to u square plus 2as. Find the displacement of this part and find the displacement of this part with the formulae and then add them. So for such sums, using a graph is so much easier. Just find the area under the graph. And then the average velocity, that is the last question, is nothing but the total displacement which you just found upon the total time, which is 260 seconds, which gives me 17.69 meters per second.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.